Friends, welcome to this video on time history analysis part 1. So in this video we shall be studying what are the types of time history analysis, what is time history analysis, how to carry it out, and we shall also solve a numerical example to understand the procedure. Now you are familiar with the analysis of the structures. This is done for evaluation of the structure, its dynamic behavior, its health, capacity, nonlinear behavior, responses, etc. We have to emphasize on the word responses. So responses will indicate the displacement response and the force response and various other subdivisions of this. It can be linear displacement response, velocity response, acceleration response. It can be strain response, angular twist response. It can be response in terms of bending moment, shear force, twist, etc. So how do we carry out the analysis? Analysis types are like this: static analysis and dynamic analysis. In the static analysis, the force you are applying is static in nature, which does not change in magnitude and direction with time. On the contrast, in dynamic analysis, the excited force is changing in magnitude and direction every time. Static analysis can be linear static analysis or nonlinear static analysis. This is familiar with you already. The nonlinear static analysis example is the pushover analysis. Dynamic analysis can be model analysis or time history analysis. Time history analysis can be again linear time history analysis and non-linear time history analysis. What is linear and non-linear we shall gradually understand as we go through this video. Now the evaluation of the system can be done either through exact solution or through numerical solution. In numerical solution you have the model superposition method through model analysis, and you have also direct integration method which will be studied in this video. This is also known as time step analysis. Integration methods are various types available in the literature: the central difference method, Hubble method, Newmark'S method, Wilson theta method, Hilbert-Hughes Taylor method, and still more. In our video, we shall be focusing on the Newmark'S method. Now, when you analyze a system, you are actually analyzing the equation of motion, which is given like this: m u double dot t plus u dot t plus ku t equal to ft. The inertia force, the damping force, the stiffness force or spring force, and this is the external excitation force. All are changing with time. So this is a differential equation that we need to solve. When you solve the differential equation, you don't get a root, but you get an equation, algebraic equation. That algebraic equation will give you the response. The response we talked about, the displacement response, velocity response, acceleration response, and so on. So this equation motion is to be solved through some method, maybe model analysis method or through time history analysis method. And you get the response like ut, u dot t velocity, and u double dot t the acceleration. And the responses like bending moments, shear force, twisting moments, etc. And the strains, stresses, and so on. When you use the exact solution, you get the exact answer to the system. But in many cases, the exact solution cannot be obtained by integration method. So there we apply the numerical methods. Numerical methods are slightly approximate, but they are applicable to all types of problems, all types of structures, and all types of excitations. We are showing here an excitation, an earthquake, which is 1940 El Centro earthquake. The up and down is the zigzagness in the acceleration are called frequency contents. What interval the frequency is changing up and down. Up and down in this figure, but in the actual physical field it can be left and right or say east, west, etc. These accelerations are given in terms of g, that is the values divided by g. So these are numerical values given here, and the x-axis is their time axis. So for different instance of time, these are available in the websites like USGS, United States Geological Survey site, and so on. And at certain interval of time, these ordinates are given. So these are in digital form. So at certain ordinate these are given. This interval of time at which these are given in the record are called record interval. Now the responses that you get is shown here. We have taken a single degree of freedom system. It has a mass and it has stiffness and some damping. You are applying some excitation here at the base, which is U double dot GD. G stands for ground acceleration. So the structure vibrates, the mass vibrates. We capture the responses at the mass level, and the responses can be displacement response, velocity response, or acceleration response, as shown by the equations here. So ut, when I say, it will have an algebraic expression on the right hand side, which is not shown here. So you will get a series of values here. After solution, you get these expressions of velocity, displacement, and acceleration values. Now we have taken a multiple degree of freedom system having 3 degrees of freedom, 3 masses, and we have applied the excitation at the base, and we get those primary response values u dot and u double dot for the first mass, which are given through suffix 1, for second mass with suffix 2, and the third mass with suffix 3. Floor, you are getting all the responses. Here pictorially we are showing the displacement response, which has less zigzagness, velocity response, which is having slightly more zigzag nature, and acceleration response, which is highly zigzag and lot of frequency content. There is closely spaced changing ordinates are there in the graph. So these are the typical responses of the El Centro earthquake we have discussed earlier. The time history analysis is also known as time step analysis, because the solution progresses step by step. With small time interval, we take the steps, and every instant of the time we solve this whole system, and it gradually progresses. So it is a time taking process, and lot of computation is involved. There will be thousands and thousands of steps in a time history, and every step you have to satisfy the equilibrium equation as given here for all the masses in the system. So it is a highly computationally involved process. We are solving the equation of motion as discussed earlier through the time step analysis. So in this figure you see, suppose this is the digital record obtained from the, say, USGS site or some site for a given earthquake. The values are given at certain discrete interval because these are digitally available. So this interval from one point to another point is called the record interval. In the beginning, in earlier days, the record interval was typically 0.02 second. Now with more refined instruments, it is much lower, so it can be 0.01, 0.001 second in record interval. So when record interval is smaller, you are getting much more number of digital records for the same time history. For the sake of our analysis, we will not analyze the system at between two, just taking the values of the record here at A and B. Instead, what we'll do, we'll split this this interval A to B in small intervals as shown in the second diagram. So this A to B we have divided into some segments, and each will be now substations of the time. This was the time station A and this was time station B, and A to B was the record interval. Now we are subdividing it into smaller intervals, and the time intervals are at small a, small b, small a, and so on. These small segmental times are called the time step size delta t. So typically a record interval will be divided by, say, 5 or 10 segments, so that the time interval for time step analysis is now much smaller. So you get a lot of time stations now, and you have to solve the entire structure with all the masses, with all degrees of freedom at every instant of the time interval. Now the time step analysis can be linear acceleration method or no, another method we'll take in the next slide. So what is linear acceleration method? We have the record interval A to capital B. Capital B is not shown here, but we have shown the segmental value A and small a coming from the previous slide. So with this small time step size, capital A to small a, the time stations can be said to be, say, Ti for the ith time step and Ti plus 1 for the I plus 1th time step. From Ti to Ti plus 1, the time is delta t, the step size. So when you assume that the acceleration changes linearly from capital A to small a in the time step interval, then it is called linear acceleration method. It is actually interpolated between capital A and small capital B and then subdivided into intervals. So from here to the A to capital B, we are assuming it to be linearly changing. The straight line is showing the linear distribution of the acceleration. The vertical axis is showing the ground acceleration u double dot gt, and horizontal axis is showing the time. In contrast, we have another method, constant average acceleration method. So here you have the time station capital A and time station capital B is not shown here, but we have shown one segmental time station small a, which is I plus 1 station. In between the time station A and small a, capital A and small a, we assume that the acceleration remains constant. And how much it is? It is the average value between capital A and small a. Whatever value at the acceleration at the point capital and small a, we take the average and we assume that during this interval delta t, the acceleration remains constant to that average value. That's why it is called constant average acceleration method. This is also used for time step analysis. Now we are entering into the Newmark'S method. So Newmark started his formulation with these simple assumptions of velocity at I plus 1 station with the velocity of the ith station and some parameters of accelerations. And displacement at I plus 1 station is displacement of the ith station plus some other parameter values. Gamma and beta are two constants assumed by Newmark, and gamma equal to half and beta lies between 1 by 6 to 1 by 4 in the analysis. Newmark's method, when we are using average acceleration method, then gamma equal to half and beta equal to 1 by 4. And when we use linear acceleration method in Newmark's method, we take gamma equal to half and beta equal to typically 1 by 6. Now in this slide we are explaining what is linear system and non-linear system. Here suppose you have the force response, so force versus displacement response. When it is a straight line response, it is a linear system. And in the second figure, the system is showing bilinearity. Here it is changing stiffness. So initially it was Ki, now it is K2. So it is a bilinear system or non-linear system. It can be also multilinear system. It can be a curvilinear system. So these all are non-linear systems. Now how do we apply the Newmark method? What are the basic things here? We take the excitation of any type. It can be earthquake excitation, it can be sinusoidal excitation, it can be stepped excitation or any other excitation. And we are applying this excitation to the system. As we have discussed, our system is a linear system where stiffness remains constant, and force displacement relationship we establish through stiffness. So if one is known, other can be found out. Or the system can be a non-linear system where stiffness will change from time to time. It changes at particular times, which are called the event points, and we have to keep track of the changes in the stiffness at those points. And because the stiffness is changing force displacement relationship is not linear, so using the stiffness we cannot get the force or displacement in a reciprocal way. Stepwise summation or cumulative values of the forces or displacements. Now we are launching into the exact procedure as given by Newmark. In this I am following A.K. Chopra's book mostly, though in the numerical analysis I have done it myself. The initial conditions are to be obtained or to be given. So at t equal to 0, from the equation of motion you can get the acceleration u double dot naught. From the equilibrium equation itself you can get the value. It can be 0 in some cases, it may not be 0 in some cases. Then you have selected the time interval. Selection of time interval we shall be discussing in the next video. Find the effective stiffness. So there is a term here which is the summation of the actual stiffness and the contribution of the damping and the contribution of the mass in the stiffness. So this combination total is called the effective stiffness K bar. And you have to calculate two constants given by Newmark. A is given by this expression and B is given by this expression. So in the beginning you can calculate all this. So here m is the mass, c is the damping coefficient, and gamma and beta, the factors you have already taken based on the linear acceleration method or average acceleration method. So this one is the initial steps we have carried out, initial calculations. Then comes the real calculation in the step 2, computation for a single time step. He calculated the effective force in the ith step, delta Fi bar, which is equal to delta Fi, change in the actual force applied, the excitation force value, and the contribution of this constant A and constant B, which is called the effective force, and involving velocity and acceleration. So we have the effective stiffness here in this expression and we have the effective force in this expression. If we divide this we get the displacement. So delta Ui equal delta F bar I divided by K bar. Similarly, velocity is given by another expression as shown here in 2.3. Then for acceleration increment, delta Ui double dot, another expression is there. Now you have got all the incremental values of displacement, velocity and acceleration. How to get the final values? Final values are given like this: ui plus 1 equal to ui plus delta ui, u dot I plus 1 equal to u dot I plus delta ui dot, u double dot I plus 1 equal to u double dot I plus delta u double dot I. All the increments are added to the previous values and you get the new values. So ui plus 1 is the new value of the displacement, ui is the previous value of the displacement. So every instant we are satisfying the equilibrium and solving it through time step analysis. Now you increase the step size and increase the time. Time will be delta t plus delta t here and go to step 2 again. So this way the things will continue. Let us take a numerical example. We have a single degree of freedom system having mass equal to this much units. The units I have not written here. This can be in any consistent units. K equal to 10 units, time equal to 1 second, time period is 1 second, damping is 5%, and the excitation is a half sine excitation here. This example is given in Chopra's book. So it is a half sine excitation, half wave, and the ordinates are given here 0, 5, 8.6 is 10 and is falling also symmetrically. So the interval between these is given as 0.1 second and there are 6 intervals. Here we shall be taking the step size also same as this, 0.1 second without splitting in between to simplify the calculation. The excitation function is given by 10 sine pi t by 0.6, which will be telling with this 0 point here and 0 point here where the ft is 0, and in between values will be obtained like this. So you have the system here having stiffness, damping and a mass, and we are now considering linear method for Newmark. So response, force displacement response of the system is linear. You have to make a little more computation of the frequency, which is k by m under root omega, and damping is not given. If it is not given, you can calculate from this twice J omega m. J is given 5%, say for concrete. Omega we have calculated, mass is given, so we can calculate the damping coefficient C. And it is up to you to choose average acceleration or linear acceleration. We have taken here average acceleration method. So gamma is half and beta equal to 1 by 4. So initial value we calculate initial acceleration equal to from the equilibrium equation, because initially force is 0, velocity is 0 and displacement 0, so initial acceleration is 0. Delta t, as I have said, we have taken 0.1 second. This is equal to the record interval here. The expression for effective stiffness, we have seen this is the expression. From here you simplify it and get the expression as 114.504. The constant A is given like this, which is 10.45. Constant B from the formula is equal to 0.5066. Step 2, computation for a single time step. So we calculate the effective force, which is given through this expression, and after simplification you get the increment in the excitation value into this constant, A into this and B into this. So delta ui equal to delta fi bar by k bar. So this is given by numerically through this expression. The velocity expression comes as 20 delta ui minus 2 ui dot. Similarly, acceleration expression, increment expression is given through 400 delta ui minus 40 ui dot minus 2 ui double dot. And we know the final values are given as the initial value and the incremental values. Now we take the solution of the numerical. Here it will not be matching with Chopra's book. I have done it myself. So initially all the values are 0. So you have the excitation value, the time value here, which goes from 0 to 1 second. In the excitation expression it is given up to 0.6 second. But after this it will be free vibration. So most steps will be there in the free vibration. Up to 0.6 it is forced vibration, and then it is free vibration. So this is the excitation force value, and this is the incremental value of the excitation force, and this is the incremental value of the effective force, then incremental displacement, incremental velocity, incremental acceleration, and the final values displacement, velocity, acceleration. So initially we have seen everything is 0 because it is a standstill at that point, and we have seen the acceleration also is 0. So this is all right. Now the force value in the next ordinate is 5. So delta Fi, the increment in the force is 5, and if you apply this expression we have got in the previous slide, so this expression ui dot is 0, ui double dot is 0, so you get delta pi, which is equal to 5. So delta Fi equal to 5 and delta Fi bar through this expression is 5. Now you get your delta ui through effective force by effective stiffness, so you get this. The velocity increment is obtained through the expression from the previous slide. Ui dot here is 0. Delta ui you have just got this much, so if you multiply by 20 you get this expression for velocity here. The acceleration increment is given through this expression. Previous velocity is 0, previous acceleration is 0, so you have only part 400 delta ui. Delta ui value is this. If you multiply by this by 400 you get the acceleration expression. In the next step the excitation force value is 8.66. So increment in the excitation force is 8.66 minus 5, which is 3.66, and through the expression of this, now all the values are non-zero. You apply all the forces from the previous line, previous calculation, and you get the delta Fi bar, and get the acceleration from the expression, displacement increment from the this expression, and the velocity increment from this expression right here, acceleration increment from this expression right here, and adding the previous value and the, for example, delta Uy is here 0.188957, and previous displacement was 0.043668. If you add this and this, you get the new displacement 0.23256. Similarly, velocity this much and acceleration this much. I think next steps will be clear, no problem. Then Fi is highest 10, increment is 10 minus 8.6 is 1.34. So through this expression, delta F bar is this, and from this expression the incremental displacement is this, and from other expressions you get the velocity increment and acceleration increment and get the final values of the time step. Next step, it is a decreasing phase of the half sinusoidal wave. So it is now reduced to 8.66. So what is the increment in the acceleration? It is a decrement actually. So 8.6 is minus 10 is minus 1.34 is the delta Fi value. So you get the delta Fi bar and get the again the incremental displacement, velocity and acceleration and other values. Next time the external force is 5, still it is reduced. So 5 minus 8.6 is minus 3.6 is, it is a decremental force, and other calculations remains as such. In the time 0.6, external force is 0. So 0 minus 5 is the change, so it is minus 5, and remaining things calculation as we discussed you can calculate here. After 0.6 it is free vibration, that is no more excitation. So these are forces are all 0, 0, 0. So increment is also 0. So putting all these values as earlier, you get the rest of the response. So up to 0.6 the responses you are getting here, these three responses are forced response, and after 0.6 these are free response, free vibration response. So I think this tabulation is clear. Thank you very much to be with me up to here. Please subscribe the channel, like and share the videos, and put your comments in the comment box regarding the quality, regarding improvement needed in the placement, and regarding any query you have about the topic. Thank you very much.